All right. So yeah, we're getting really close to the end now. We're going to be looking at circular buffers, or I more commonly know them as like a ring buffer. And basically the way it works is pretty simple. Where basically you have a ring, and when you start to get to overflow, instead of in our linked list case where you'd add one, or in an array case where if you try to use more, you get a buffer overflow. Instead, what you do is you go back to the beginning. And that's all it is to make a ring buffer. And we're going to be using that for our undo move data structure. And the reason why is right now we're allocating memory dynamically when we actually just don't need to do that at all if we use a ring buffer. So that's what we're going to do. We're going to make a ring buffer. And to do that, we're going to create something called temp.cpp. And I'm going to put it in here. And temp.cpp is just going to be like this, and it's just going to be a test file, really. And since we're not using an actual like testing framework like Google Test or something, we're just going to be using like asserts everywhere. And then we'll just do hello. I know some people like world, but whatever. And then if we do make test.cpp, or src, sorry. Nothing to be done for, oh, oops. So we're doing this ourselves, and let's also have, it'll be like std equals c++23, just because. And then when we run ./a.out, we get that. And we're good to go. Cool. So the next thing to do is actually implement our ring buffer, ring buffer.hpp, and all I'm going to be doing is I'm basically going to be just copying this little interface we have because we don't need anything else. I don't know if we call clear other than no, we do. Okay. So we will be using all those. So let's just start taking those where they're relevant. And then we can take that. And then it's just push front, pop back. Okay, cool. And do we use like push front? So we don't really use the push back stuff. We use push back, and then do we use pop back? And then we use pop back. So we'll use just like push and pop, and those will be ours. The other ones are a little bit more like linked listy, if you will. And then we also want void pop. Okay, cool. So let's do our thing. Part of me, by the way, wants to do this kind of style because I've been reading, there's like Casey, actually this is exactly the one I wanted to look at. There's something that I've been reading recently that I hadn't heard before until I came across it in the Better Software Conference. And if you're curious, they have like a software conference. Yeah, they have like a YouTube channel right here with a bunch of talks. So like there's like the Casey Muratori one, the Ginger Bill one. Do I see the one? Yeah, this is the one that I was looking at the other day. And they talked about compression-oriented design, which I'd never heard of. Obviously, I'd heard of like, or compression-oriented programming. I'd never heard of it. Obviously, I've heard of like object-oriented programming, or oops, in the little joke right there. But yeah, I'd never actually come across it. And so I was reading through this, and basically what it's showed me, actually I can go back. What it showed me was there's this naming convention that Jonathan Blow has for classes of where you capitalize the first, or classes structs, whatever, right? And then you do an underscore between the capital. And I don't know if it makes something objectively better in terms of like it's more readable because it follows this style. But there is part of me that really likes it. Now, because everything else in here is not following that convention, we're not going to follow that convention. But I wouldn't be surprised if at some point we go back. Oh no, I actually want temp.cpp. We go back and actually change that. So we're gonna do the next thing is we'll do a template type name t. There's also a there's also another way you can do templates, which is like class t. And I'm not exactly sure what the difference is, like what we're actually getting. So that's something I would like to do a video on at some point, partially just because I think it would be interesting, but also so I can learn exactly what the differences are. So we can do this, we can do this, we can do this, and then we also are gonna want like an std : size t. And actually this, no, I'll come back to that later. So size t and then size. And so we're using this like to basically say when we actually make our ring buffer or the data structure beneath the ring buffer, we'll have like a t data like this, and it will be of size. Right, so that's the initialization of our data. And there's actually nothing more to do. We're not going to increase the data. We're not making it dynamic. We're not doing anything like that. We are just going to do that. And the other thing to do, size t, I think it's just index. And we'll zero it. We'll put it at the front just because I feel like it's good practice. I don't think it really will matter for packing in this case, but just as a general rule, I just always put it front. Like the smaller things at the top and the bigger things at the bottom, but you could also be smarter about it when you're thinking of like, this is 32, this is 32, and if these two are 16 and 16, we could put them next to each other or something like that. Anywho, all we're gonna do for clearing is we're gonna make the index equal to 0. I know in our other one, when we cleared, right, there was like a big procedure where we have to delete things and do stuff with our objects and get rid of stuff. But in our case, we just have this thing. We don't care about what t is. We could, I know in like C# we could do like data 0 equals default, but that's not a real thing in C++. Maybe there's like a default value for template. Default value for template? I don't think so. And honestly, even if there was, I don't think we really want to set the default value. I think we're just fine doing this. So we have this data. We've already signed it over. So this is just going to be like a copy, really, where we copy the data into the other thing. Or we could play around with like a move or something. I don't know. We'll come back to that in a second. We're going to have to do some acrobatics. Well, do we actually have to do any acrobatics? I think it's just data index is what we're at. Because that's like our size, so it's always going to be like one ahead almost. So if like, I'm just thinking out loud here, but we're going to just like have data is equal to, I don't like this, right? There's new data, and then we could also, just to be clear here, this could be ring buffer, right? And then this will be, now we can actually just make this data, and that's totally fine. Data, and that just works. And then what we need to do, right, is we need index is equal to index plus 1. But then what we need to do is we need to mod it by the size. And so that basically makes it so if we're all the way over here at the end, it will come back to the beginning, and then we'll just go, and just keep going. Cool. So the next data structure thing to do is a pop, because we do use that, where basically what we're going to do is the exact opposite almost. We'll have like a ttemp is equal to, well, actually, now that I'm thinking about it, we'll have std size t I is equal to index, and we'll return ring buffer I, but we're not actually going to change anything in that data, if you recall. So then what we do is now that we have this, what we need to do is we need to update index. So index is equal to index minus 1 mod size. And the one question I have here is if I have like -1 mod 100, do I go to 100? I go to 99, which feels right because the size is going to be 1 larger, so that's exactly what we want. Okay, cool. And I know I just use Python, but the mod behavior, to my knowledge, is no, it's just math, so it's just going to do that. Okay, so that's that. I think that's really all we need, which is kind of nuts when you compare it to like all the time we spent on this linked list and we pulled it and everything. But if you recall, like this already is the pool. There's nothing to like add or remove, and we're just like moving along our index and doing our thing. Okay, so we're in here. So let's do ring buffer. We'll do of type float. Why not? And we'll make it size 1. RB1. And what we're missing, why this is all squirrely, is we need to do include ring buffer. And then what we'll do is we need asserts, so we'll do that. We'll separate this, even though we really don't need to. And we'll do rb1.index equals 0, right? And then what we'll do is rb1.push, and we'll push 32f, right? Something like that. And then we'll do, we don't need the IO stream, it's just going to bother me. Okay, so now what we want to do is we want to assert rb1.index is equal to 1, right? Because that's our control flow. And we also want to do rb1.ringBuffer 0 is equal to 32.f. And now if we run that, I really just should do like and because that way I don't even have to think, and we're not really compiling anything crazy. So we failed on this one where we're saying this should be equal to 1, but it's not. So of course now I actually do need to see out, unfortunately. rb1.index. Then we can like endl it. Now we can do this, and we can see it's still at 0. So we did a push. We can go to that definition. Index is equal to that. And basically what it's saying is that it's just going to be overwriting it. So really that is the correct behavior when you actually think about it. So we'll delete this, and then we can do this again, right? We'll do that, we'll do this, we'll do that. Because if it's size 0, just for context, like it's not going to actually, we can do like -1.1, why not? If it's actually of size 0, there's nothing to be done. So like if we wanted to, we could have like an assert, somewhere in the template. I think there's a way to do it where we could assert that the size must be greater. Well, it's not, it's a U size, so it can't be less than 0. But if it's size 0, there's really nothing to be done the whole time, so it's just gonna, yeah. I guess that is actually like, it does float temp 0. Temp 0, this shouldn't work, right? I'm just kind of curious from like the language perspective, like what actually happens. And it just prints out 1, which is fine, I guess. Because like really, if I do like R1, right? Well, it's not like we're in Rust where there's going to be like a problem. We're just overwriting memory super dangerously. So I guess, yeah, that makes sense. It would be nice if there was some template arg exception C++ maybe you can do. We'll just go Stack Overflow. And it looks like what you can do, size tn. We don't love that. All right, so my takeaway is that there's definitely a way to do it, but we're just going to skip it for now. And if we really want to make this a lot safer, for right now it's only me and you using it, so I think we'll live, but we'll put in a to-do size check size such that size is greater than 0. Okay, cool. So that's good. Now we can do the next ring buffer. We'll just do like an int. And for this one, we'll make it size 10, right? And we'll do RB2. And then what we'll do is for int I is equal to 0, I less than 11 plus plus I, right? And then we're just going to do RB2 dot push back, or not put, just push. And it's going to be I. And then what we should get is if we do assert, the rb2.index should be equal to 1, right? I think we'll come back to that. And rb2.0 is equal to 10. You love it when you're guessing. And then we'll do like ring buffer. So really we should have like a way to access it. Sorry, 0. Because I don't like writing rb2.ringBuffer every single time. So that passed. So what I want to do is there's like, we could override the operator like this. It's a very C++y way to do it. But I also know a lot of people seem to be really against operator overloading. But for me, this feels like a good case for overloading operators. So if we just like look into it real quick, right? Like all we do is we just do this. That seems to me like a very good, what is this? Struct swap them static. That's interesting. Okay, whatever. So we do this. We don't want static. And we are going to return type T. And I don't know why it's got this. We want this. Oh, it was, I got that. Okay. So, and then we're just going to return, not T data, right? It's going to be like size T I return. And this is super unsafe, right? In our ring buffer context. Because one, we could have too large of a thing, right? If they like pass size 100 and we have a ring buffer of size like 2, then that will cause a problem. But maybe we'll like add some like asserts or something to be a little bit smarter in like a debug mode at some point. So let's actually do that. To do, add debug mode check, and then add, well actually, because asserts will go away when we do like a production build anyways. So we'll just do ring buffer I, right? And then what are actually the asserts that we care about when you think about it? We have CS assert, right? Cool. So in this case, we need I to be, I cannot be less than, it can't, because we're doing a size T, it can't actually be less than 0, so we don't care about this. It's less than size. Otherwise, it's safe, it's just not necessarily ideal. But we can't necessarily do like a if it's less than index unless we start checking for overlapping. So this is kind of the best we can do for right now. So we're just going to keep this there. And I think that's fine. Yeah, we'll just do that. So we'll see if it actually worked. So we can get rid of this, right? So now we're also checking our little overload right there. So now if we do it, perfect, it's still working. And what I really want to do is I want to do one more check where I can do like rb2.push 10. So we're going to keep this correct. And we'll do assert index is equal to 0. Well, we can actually make this. is equal to 0 and RB2. So this is actually right there what we want. Otherwise, we want to do asserts in each one. RB2.index is equal to I, and RB2, I see that error, I'll come back to it in a second. RB2, and then, oh, there it is, yeah. Index is equal to I, and then we do that index is equal to this, and I'm expecting a bug, if you will. Yeah, what is the problem? No visible overload for RB2. Is it because, oh, there's no index, oops. RB2.index minus 1, which will just be I. Okay, and that failed for this one. And that's not surprising. I know I just have like one problem here, where if it's 0, it should be 0, which I stand by. Index should be equal to plus 1, though. Except for in the last case, right? Because I thought I was covering for this. Index I, and we'll just leave it like there for now. That's fine. So 1, 0, 1, 0, and then we get to 0 over here. And 9 will push it forward. So what we really want is like this mod 10. And that will pass all of our cat tests. So that's our ring buffer actually just working, which is pretty cool. Now, what I'm not gonna, well, actually, let's do it real quick. So I'm gonna just take this and put it in the README. We'll do like ring buffer test code. We'll do C++, put that in there. So now it's somewhere in case we want to come back to it. RM src temp. So now what we can do is in our, right, we have a couple cases where we use it. What we can do is we'll keep this, but what we'll add is a ring buffer, and we'll make it a of type command, right? And then we have our max commands. And what's max commands again? We'll come back to that in a second. Commands. And the problem right now is it doesn't actually have ring buffer HPP. Now we are expecting a few compiler errors, maybe. So we don't have a dot size over here. So what do we want to do? Okay, so this is a little bit more obnoxious than I would have hoped. Because what we're going to do is we're actually going to do like a speed test at some point, is what I was hoping to do. But let's just do... Okay, so I don't actually really care about like this commands.pop front stuff anymore, right? Like it's interesting. What actually is max commands even? Yeah, okay. So we're just gonna comment that out. Node linked list approach, because we're gonna come back and kind of clean this up a little bit, in just a little bit. Commands.push. Yeah, so it's not as clean as I would have liked, but that is okay. So this is just push back. This is just push. And this is just pop. Well, we actually don't have a pop back. It's just pop. Yeah. All right, and so this returns. Oh, did I ring buffer is returning of type T. Oops, there we go. Make There we go. Sorry about that. Line 30, just push, push. Anything else? Nope. Now we go to here, line 53. And if commands.size is greater than 0, we do this. Commands.size is greater than 0. Right. Okay, so yeah, so we are actually in a weird place right now when I think about it. So much so I'm thinking of not even just using the ring buffer. And the reason why is basically I see this right here, and I see that like when we start to overflow, right, we need a way to actually stop. And what I mean by that is like if we have like 1, 2, 3, 4, 5, and then we overload into 6, 7, then the player starts pressing undo a bunch. We need to stop at 3. And we need a way to be able to like mark like this is the last valid place to undo at. And so what we can we can actually solve that, right? So we can have size t last valid index is equal to 0, right? And then when we actually start to overload, or not over, when we start to like go over, we actually need to handle that a little bit more intelligently. So we know like the valid range of where we are. So like if, for example, like this is the end and this is the start, right? We'll only go to like here, for example. So we have our index is equal to 0. So that means, is this even the right? So like last valid index is equal to 0. Yes. And then over here is where we actually need to get a little bit smart. So what we're going to do, I think, is actually leave this for the next video, because I see we're at like 28 minutes, which is just a little bit longer than I would like, to be totally frank. But we're in a pretty good place in that I'm a little bit confused in like what's the best way to go about it. So I don't want to waste anybody's time. But 2, it's something for you to think about if this is interesting to you, and you can come up with a solution. I'm sure there's like a really easy one where if we do like if index plus 1 is greater than or equal to size, right? Which is what we're going to have to do, right? We do index is equal to 0, and then we can do like last valid index is equal to index plus 1. Feels actually kind of right. And then in this case, right, if we're going backwards, then we need to do something a little bit differently where, well, actually, is that just it? I think that may just be it. But we're definitely missing some edge cases where when index, if we like go all the way back to the beginning, maybe we're not. Maybe this is just it. I don't know. I do not know. It's something worth thinking about. But let's go into here. And then there's like app state. I don't know. That could just work, frankly. I think it won't, but. So we'll just do this. We'll just do this one. Boom, boom. And that's working, but you can see it's not fully working, right? So we have this little bug where it's not taking us all the way back to that final one. And so, yeah, there's a bug here to fix. I think if we just frankly, there's definitely like a, where'd it go? I want the game C++, sorry. There's definitely a way to do it where like it's like -1 and we can kind of just cheat it. But that to me feels, yeah, it's not gonna work anyways. Okay, so this is where we're gonna leave it. There's this bug, this is the bug, so that's a really useful message for all of us. But this is basically where we're gonna stop. Essentially what we have is we have this problem of identifying the start of the ring buffer. So right now it's 0, but once you start to actually make it bigger, where index plus 1 is greater than or equal to size, we get this weird thing where last valid index, yeah, we just have this little weird bug where we're having trouble identifying exactly what is valid in the ring buffer and what isn't valid in the ring buffer. So we'll fix that in the next one, and then we'll also do a speed test to actually compare which one's better overall. We'll make a little like a temporary file again, C++ file where we will, there we go, compare the two. And we should hopefully see that dynamic allocation is slower than stack-based. So yeah, I'll see you in the next one. Bye.